Hello, my name is Chen Griner and I'm a PhD student from Ben-Gurion University of the Negev. Today I will talk about our paper Cerberus, the Power of Choices in Data Center Topology Design, Throughput Perspective. This work is a joint effort by a great team of people from Ben-Gurion, TU Berlin, TU Munich, and MIT, which are all listed below. Today, data centers are an essential part of our daily life. More and more applications and services are reliant on data centers. The amount of traffic served on data centers continues to grow and requires new and better technologies to solve the growing demand. But traffic is not only growing, we can also see it has structure. Traffic matrices seen here from Facebook and Microsoft both show that traffic is sparse and skewed. Not all destinations have the same demand. Furthermore, looking at traffic from Facebook in a temporal scale, we see that traffic is not uniform, that is, it has bursts of traffic. A typical solution for data center traffic is a demand-oblivious topology. These come in many flavors, for example, the fat tree, which you can see here, but they all have something in common. All network connections are predefined and are unchanging. These topologies are good for worst-case traffic in the sense that they are never very bad, but much like this highway, they cannot adapt to changing circumstances. Some links could be congested and other underused. Furthermore, when faraway nodes communicate over several hops, it can be problematic, especially for large flows. The more hops a flow must traverse, the more network capacity is consumed. This inefficiency arising from multi-hop routing can be seen as a bandwidth tax. New emerging alternatives in networking are demand-aware dynamic networks. These topologies can change their connectivity during the operation of the network. One such example is a recent proposal by Microsoft called Project Tor. This network is made from two layers, an upper layer which is made from mirrors. These mirrors are then able to redirect beams of light, much like the light carried by optical fibers. They carry network traffic. The beams are sent from a lower top of the rack layer or Tor layer for short. This layer allows connection within the network. How does this work? Assume we're given the following traffic demand matrix. Here, red squares denote communicating pair and black squares denote no traffic. Notice that this matrix is sparse, much like the real-world matrices we have seen before. What will the network do? The network will adjust itself in the specific pattern, to match the specific matrix, to create an optimal network where all nodes are connected with a single hop, thus incurring no bandwidth tax. What happens when we encounter a different pattern? We get a differently connected network that matches demand again. Sounds great, but is it possible? Yes, today a spectrum of different technologies exist with different sizes, shapes, and reconfiguration times. But as always, there's a trade-off. Transitioning from one configuration to the other takes time. We can think of this time as a latency tax. Much like the bandwidth tax, it hurts the performance of the network, lowering throughput and increasing latency. A network which is constantly reconfiguring itself might not benefit from this technology if most of the time is spent on changing connections and not for solving them. Therefore, the reconfiguration needs to be cleverly planned to improve performance. To our knowledge, there is no unified model which allows us to compare dynamic and static networks in a single framework. We therefore propose the following. Our data center network model is based on the basic structure of the demand-aware network. It relies on a two-layer leaf-spine network architecture. The Tor layer has N leaf switches, and the spine layer has K optical spine switches that can be of different types. In the optical spine, each switch has N input and N output ports. For example, when traffic needs to be routed from the fourth to the fourth rack, flows can take the following one-hop path. Note that inside each switch, the rack can connect to any other. But as we see inside each switch here, they only support one matching of in and out ports at a time. We therefore refer to this model as a Tor matching Tor network model. Using our model, we can represent several network topologies, demand-aware or demand-oblivious, static or dynamic. These topologies can be defined by different switch types in the spine layer. Let us explore our different topologies. The first topology we will show is ExpanderNet. Following a recent proposal from Connext, the spine switches here are static switches. The topology is configured once and then remains in this configuration permanently. While it can be configured with many different known topologies, we use a random graph which creates an expander. On this expander, packets are routed along multi-hop paths as they would be on conventional networks. As we can see, this network is static and oblivious, but since no online reconfiguration is made, it provides low latency for all communications. Second topology type is RotorNet. Following a recent proposal from SICOM, all spine switches here are rotor switches. Rotor switches rotate between different matchings with reconfiguration times in the order of tens of microseconds. The sum of these matchings emulates a complete graph using time division. Inside the network, packets are routed either with a single hop or two hops using variant routing. That is, packets are either sent directly to the destination or indirectly via intermediate random node. This network is dynamic since connections change over time, but it is also demand oblivious since the order of matchings is predetermined and the traffic pattern doesn't affect it. The fourth topology type is the demand-aware net. Following the recent proposal from Project Tor, all spine switches here are demand-aware switches. These can create arbitrary matchings in any order and will respond to traffic demand in an online manner. This comes at the cost of a slow reconfiguration time in the order of tens of milliseconds. Inside this network, packets are routed with a single hop. Using more is possible, but the exact algorithm to do so efficiently is a subject of ongoing work. To conclude, this network is both dynamic and demand-aware. Each of the topologies I presented has different pros and cons. Let's first look at the awareness dimension of the topologies that we just saw. Firstly, the demand-aware net. It is optimizable towards specific traffic at the cost of being slower and more complex. Large elephant flows might amortize these costs. RotorNet, by its nature, is good for all-to-all traffic. Since it is oblivious, it can be very fast and should have a simpler control plane. It provides periodic direct connectivity and should be good for all-to-all traffic. Lastly, due to the faster reconfiguration times, RotorNet pays less latency tax when compared to the demand-aware net. What about the flexibility dimension of networks? Dynamic and static networks also have their own pros and cons. Static expander net is good for traffic that requires low latencies, since there is no need to wait for reconfigurations. While dynamic networks like RotorNet and demand-aware net are able to serve flows with high throughput due to their direct connectivity. We can say that in dynamic networks, we pay more latency tax, while in static networks, we pay with a bandwidth tax. To summarize, we can plot the location of each of our topologies on two tax axes in this manner. To amortize tax costs, we would like to send latency-sensitive small flows to the static topology, medium-sized all-to-all traffic to the rotor topology, and large elephant flows to the demand-aware topology. Clearly, we see that flow size matters. What are the actual flow size distributions of real-world traffic? The following figure contains a CDF of several real-world traffic distributions. We can make several observations. The first observation is that most flows are small, but most bytes are found in the big flows. For example, in web search, we see that half of all flows are smaller than a megabyte. The second observation is that the transmission time of each flow depends on its size. Here we see the speed of transmission on a 40 gigabit per second link. The third observation is that for smaller flows, we cannot amortize the reconfiguration time with current technologies, since this time is longer than the transmission time. Finally, the fourth observation we see is that for larger flows with transmission times closer to 1/10 of a second, reconfiguration time may be amortized. Using these observations and the known reconfiguration times we discussed before, we see that all types of topologies are necessary. Different areas of the plot mark where the use of each topology is optimal. Now we can finally discuss Cerberus. The basic structure of Cerberus is the same as all of the other topologies. However, Cerberus is a hybrid network. It has a different switch allocation for each topology type: KS static switches, KR rotor switches, and KD demand-aware switches, whose exact values will be determined later. Static switches are used throughout latency-sensitive small flows. Rotor switches are used throughout all-to-all traffic of medium-sized flows. Demand-aware switches are used throughout large elephant flows. After establishing the structure of Cerberus, let us discuss the main metric we analyze in our paper, throughput. We follow previous definitions of throughput from recent paper. We start with a given demand matrix T. What is then the expected throughput of a network? We denote as theta of T the maximal scale down factor by which traffic is feasible, when this factor is between 0 and 1. If theta of T is 0.5, we can scale down the demand by half and solve the resulting demand within 1 second. The throughput of a network, which is denoted as theta star, is defined as the theta of T for the worst case T, i.e. traffic metrics of this topology. Based on these definitions, in the paper we present a complete mathematical framework we developed. This framework allows us to evaluate analytically the performance of optical switches, considering real traffic distributions. Based on our models, we formally show a bound for the throughput of each of our three component topologies. Let us shortly discuss those. For ExpanderNet, the throughput is bound by 1 over the expected path length for the flows. This network only pays a bandwidth tax. The throughput of RotorNet is bounded by this formula. The right part of the formula represents the latency tax. This is essentially the time spent on reconfigurations and waiting for the correct matching. The left part represents the bandwidth tax. Since we use variant routing, some packets are sent at 1 or 2 hops. Phi of t, the skewness parameter, represents the portion of flows sent at 2 hops. Note that this is the first time an analytical bound for the performance of RotorNet is found. To find theta star, we use the worst case traffic matrix for RotorNet, which is a permutation matrix. In this case, nearly all flows are routed with 2 hops. This results in the following bound, which means the throughput of RotorNet is no more than 0.5. Conversely, a permutation matrix is the best case demand matrix for demand-aware net. In this case, all pairs are directly connected and only minimal tax is paid. The full details of the formula are found in the paper. So what is the throughput for Cerberus? In short, Cerberus is optimal when the throughput of each network component topology is the same. That is, it is balanced. Otherwise, this would mean we have wasted bandwidth and we should have shifted resources from one network to the other. To achieve a balanced network, we need to find the optimal switch allocation of each topology. For example, K star D is the number of demand-aware switches in the balanced network. We also consider other parameters. Among these are the demand-aware switch reconfiguration time and the mean flow size. In the paper, we also show that Cerberus achieves better throughput on the data mining distribution and also for a permutation matrix. Note that the worst case throughput for Cerberus is not known. In summary, the full details of all parameters and our throughput analysis is found in the paper. Let us now focus on one aspect of our results: demand completion time. In short, it answers the question of how long does it take to solve a given demand matrix. In this figure, we see the results for demand completion time of 3 networks: RotorNet, ExpanderNet, and Cerberus on a real-world workload. If we know the demand completion time, we can bound the throughput. It is simpler to compute demand completion time since we can account for waiting time or tax more easily. For example, the throughput for Cerberus in this case is 0.8, while for RotorNet it is 0.6. and for expander net, it is about 0.5. We see that Cerberus can achieve superior demand completion times with better throughput compared to either of its component topologies. In the paper, we also run flow-level simulations to validate our results. In conclusion, different traffic types will be better served by different topologies, depending on flow size. Our work also sheds more light on the trade-off of existing topology designs. Cerberus shows that combining several different switch types and algorithms and directing traffic for the most appropriate topology, we can improve network performance. The previous figure has also shown that Cerberus could be better than the sum of its parts. This is clearly just the tip of the iceberg. Many challenges remain, better simulations and a larger prototype. We also believe that developing more complex algorithms for demand-aware networks is possible and will allow us to gain further improvement by, for example, using multi-hop routing on the demand-aware topology. Further studies needed into the effects of network structures such as that of Cerberus on congestion and routing algorithms. Finally, I would like to thank you for listening to our talk.